similar to the equilibrium constant expression. Use the same format. We're dealing with heterogeneous equilibria. So because of that, we will be excluding pure solids, as in this example that we did earlier. So let's find the solubility product constant given the concentrations of these two ions. We have strontium fluoride, and so first I'm going to write down, of course, what I have, the SR2+. Concentration is 8.7 times 10 to the negative 4th molar. Fluoride, 1.7 times 10 to the negative 3rd molar. Now, my solid here is SRF2. So we're showing the dissociation of SRF2, strontium fluoride. And so we'll need to remember the ions that those form. Strontium forms a 2+ charge based on the pattern in group 2A. And of course that's right here as well. And that's going to be aqueous. Fluoride, based on the pattern, forms -1 charge. Aqueous. Now what about this 2 right here, the 2 subscript? Well, that means we need to put a 2 coefficient in front of the fluoride. So here's our dissociation equation. Now, next we can write the solubility product expression. KSP stands for the solubility product constant, is the product of the SR2+ and the Now this 2 becomes the exponent. Now do we need to divide this by the SRF2? Well, no, because that's a solid. Look at the state of matter. Remember, we don't include pure solids or pure liquids because their concentration is constant. So we set their concentration as equal to 1, and it drops out. All right, so now it's just a matter of putting in those numbers that are given to us. So we have the concentration for strontium, and likewise for fluoride. And so this is very simple. We just need to multiply those two terms together. Now be careful with your calculator that we do the order of operations correctly, of course, so we need to make sure that squaring occurs, the power occurs before multiplication. Here's a way to make sure that happens right. 8.7e or negative, so here's my first number, times, open parentheses, 1.7, oops, I just typed the wrong thing, let's try that again. 7. Open parentheses, 1.7 times 10 to the 3rd, then close the parentheses, then press equals. So that's just telling your calculator to make sure to do the power first before multiplying. All right, and so there's our solubility product constant. So it's the same thing for other problems. For instance, if we did this next problem here, number 2, you could give this one a try. I'll put up the solution in just a minute. Similar approach to this problem. And so here's the solution to number 2. So again, we have the concentrations. We write the dissociation equation. And so then we have the solubility product constant here as we substitute those numbers. And that's it. All right, let's go on to another topic. The molar solubility and we're going to use the symbol S to represent that. So the molar solubility is basically the solubility of each ion in molarity of a saturated solution. So all right, so this is a way of calculating solubility. And to find this, let's try this example. We're going to find the molar solubility of lead sulfate given the solubility product constant. So we have KSP. KSP is 1.6 times 10 to the negative 8th. We have the equation here, and our unknown is S for molar solubility. So let's write our dissociation equation. Lead sulfate dissociates to make lead. Now what's the charge going to be on lead? We could maybe work on some scratch paper and figure that out. So lead, of course, in lead sulfate, we can figure out the charge of lead by using the charge of the anion. We know sulfate is 2 minus, so therefore there's a total of 2 minus charge. There must be 2 plus charge then, divided among 1 lead, makes each lead have a 2 plus charge. So we know it's lead 2 plus aqueous and sulfate. So now that we have this expression, we can just go on to write the solubility product expression. So we have KSP is PB 2 plus times sulfate. So to find now the molar solubility, we're just going to substitute S for molar solubility into each of the concentrations. So S times S. So KSP then is S squared. And so now we just need to do that. And we can take the square root of both sides. So that's going to give us S, flipping this to the left, is the square root of KSP. Alright, so we just plug in our numbers. Okay, 1.6 times 10 to the negative 8th. Take the square root of that. And that comes out to 1.2 times 10 to the negative 4th molar. Let's look at one additional topic now. The common ion effect. So the common ion effect is an application of Le Chatelier's principle. Let's take this first example. So if we have the salt Na2 C2O4, and we're going to show the dissociation of this. So we have 2 sodiums, and then we have 1 C2O4 for the chromate ion. Now, if we have, we have calcium chromate. So our actual equation is calcium chromate. So we also have some sodium chromate being added. Let's go ahead and write the actual equation though. Do that in orange. All right, so we actually have a couple of things going on here. There's calcium chromate, and there's also sodium chromate. Now we're given the solubility product expression for the calcium chromate. We're given the constant for that one. But then it says that it adds some of this too. Now notice that when we show the dissociation of both of those, there's something in common here. So not the sodium and calcium, of course, but this thing right here, the chromate ion, is in common. They both share chromate. So by adding the sodium chromate to a solution containing this in equilibrium, it stresses the system according to Le Chatelier's principle. It adds more of this increases, the chromate ion increases, and there should be 2 minus here. I forgot to put the charges on, so there should be 2 minus and 2 plus and 2 minus. So it increases the amount of the chromate, which stresses the system, and according to Le Chatelier's principle, means that the system is going to shift towards the left, and thereby it decreases the solubility. So the solubility goes down as the system shifts towards the left. So for our problem here, these can be certainly more complex, but problem. We really approach this in basically the same manner we just approached the earlier problem here, because our problem gives us the concentrations after the common ion is added with the original amount. Sometimes in later chemistry classes you'll have to figure that out, but for our purposes right now, it makes it easy for us. We're given the total amount of the chromate, and we're given the constant, and we just need to find an unknown here. So we solve it in a similar way. We write our expression, KSP. Let me use a different color actually. So KSP then is the calcium ion times the chromate ion And so we just solve for the unknown. We have calcium as the unknown. So calcium then is the solubility product constant divided by the chromate ion. And our problem makes this very easy because here we have the concentrations of all of those. Chromate is given to us right there, and the constant. I'm just going to transfer those numbers, plug in those numbers. So the solubility product constant, 2.7, times 10 to the negative 9th. Right, so that's right there. And then the concentration of the chromate is 3.5 times 10 to the negative 2. All right, so that one is right there. So our problem is also giving us the total amount of the chromate from the sodium chromate and from the chromate and the chromate from the calcium chromate. So it's actually adding both of these when we think of this number right here. So this number is inclusive of both of these, the chromate from the sodium chromate and the chromate from the calcium chromate. So that makes our job quite a bit easier here. All right, so just a matter of simple algebra. Just need to divide those terms, and that would be it. All right, let's try that one more time. And that comes out to 7.7 times 10 to the negative 8th. Concentration unit, capital M for molar.